the Sustainability Management Master's Program, you are answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact. It's a pleasure to introduce today's speaker, Dr. Andrea Copping. Andrea is a senior researcher and advisor at Pacific Northwest National Laboratory and a distinguished faculty fellow in the School of Marine and Environmental Affairs at the University of Washington. So she's on the other coast. Her research focuses on environmental effects from the development of wave and tidal energy and offshore wind installations. She leads a research team that integrates laboratory field and modeling measurements into a coherent body of evidence to support siting and permitting decisions. So Andrea holds a BSc in marine biology from McGill University, Canada's top school, and an MS and PhD in biological oceanography from the University of Washington. So today, Andrea will talk about the impact of marine energy installations on the environment and the people. Andrea.
Thank you very much, Dibs. And thank you, everybody, for inviting me here to this distinguished seminar series. And you have a wonderful set of sponsors who are here. And I know none of these things happen without the sponsors. Let's see, go to the next slide. There we go. So what I'm going to talk about today is moving forward with marine energy, but the need to think about the environment and the people involved. And I am, as Dib said, representing Pacific Northwest National Laboratory, which is one of the U.S. Department of Energy's national labs. We're out here on the Pacific Coast, Seattle, Squim, etc. I am also representing an international organization called Ocean Energy Systems Environmental, and I will talk about a bit about that a little bit later. So what I want to talk about today is marine energy, that it's a new way to capture energy from the oceans. I want to talk about the importance of environmental effects and social concerns. I want to talk about some of the work we do as OES Environmental, the history of how we got to where we are. It's a fairly short history, but pretty up and down, and some strategies we use for understanding the data and the information coming in on environmental effects. I'll spend some time talking about the state of current knowledge, which we have been published a large report recently, and then talk a little bit about where we see going with environmental effects work in the future. To remember how Zoom works versus Teams. Okay, so marine energy. I know many of you are engineers, you are business majors, and some of you may have come across marine energy, but it's not something that's well known. So we define marine energy as a new use of the oceans, using energy harvested from waves, tidal energy, the persistent ocean currents, things like the Gulf Stream, but also gradients in the ocean, either thermal difference in temperature or difference in salinities. And for each of these technologies, there's a very different and distinct set of technologies to address these ocean energy sources. And there's just a few of them pictured here. The two pictures on the left Core Power and Mutrika are to capture wave energy. The Core Power one goes up on its side and bobs up and down. This is a very common one, following the motion of the waves and then having a generator involved. Mutrika is actually a breakwater in northern Spain, and they have put a series of these devices into the breakwater, so as the wave comes in, it generates power, goes back out. In the center, Mackay Engineering in Hawaii is pursuing ocean thermal energy conversion, or OTEC, where they are looking at the differential through a heat exchange process from warm surface water to cold deep water. Down in the bottom red stack, what you're seeing here is the mouth of a river. As fresh water enters saline water from the ocean, you can generate power across a membrane. Then over in the upper right is the largest of the tidal energy devices in the world, the Orbital O2. And what you're seeing is a floating body with those two turbines out to the side. They get lowered below the body, and then they turn with the tides. And then another sort of version of that in the lower right, Ocean Renewable Power Company, ORPC, has got a river version. This one floats with that down near the slightly subsurface with that turbine turning with the movement of the rivers. This is large rivers. This has nothing to do with hydro dams, but rather placed in an open river. So there's many, many different ones, especially among the wave devices. But why should we bother developing marine energy? Many of you have heard of offshore wind, which is much larger in terms of megawatts, and we're not there yet. We do know that if the world chose to go to renewable energy tomorrow, we could probably accommodate 80% of the need around the world with solar and wind. But there's that other 20%, and this is really where marine energy shines. We know there's huge resources in moving water and gradients in the ocean, and this could really help many nations that have coastal areas or even very large rivers. In addition, marine energy has some unique capabilities where these others, solar and wind, really do not. For instance, at high latitudes where solar panels don't work so well, especially in the winter, and actually wind devices have a really hard time in Arctic and Antarctic conditions. Plus, we can generate power at sea and use it at sea for things like ocean observation platforms, everything from navigation buoys, weather buoys, autonomous underwater vehicles, etc. Never bring the power to land. Offshore aquaculture, which is becoming where most nations are going further offshore, etc. And if you look at many of the remote coastal areas and islands that are all generating power with diesel, this is an ability with a microgrid and with energy storage, marine energy, maybe a little solar, maybe a little wind, but to really bring those together. And the marine energy is very predictable on the whole, much more so than wind and solar. And this is a way to really help bring energy justice to many of the small countries, many of the small islands of the world. I keep forgetting I can't do that. So, but what do we need to do? Supposing you want to create a marine energy device, get it in the water and start generating power. There's a lot of things you have to consider. You have to do your resource characterization, figure out how much power is really out there in waves or tides or whatever you want. You have to think about where you're going to site it. You have to do some tank testing, your engineering designs, and then test them in tanks, make sure they work. You you need to worry about, oh, what's going on here? Why is that not working? There we go. You have to think about mooring it, either putting it on the bottom of the ocean or having mooring lines and anchors that will keep it in place. You have to make sure it's survivable in these very high energy ocean areas that are really tough to deal with. You have to fabricate your first prototypes and your first test ones, and eventually worrying about manufacturing many, many devices. You have to worry about financing, obviously. Also, community engagement. You want the community to be on board with you, not against you. And you need to think about environmental effects. And you can, if you don't really think about this in advance, it can all come crashing down. You need to get regulatory permission, but even if you get all the other stages right, nobody lets you put it in the water because of adverse environmental effects or uncertain environmental effects, then you've really achieved nothing. So we really try to look at this in advance. So why should we look at environmental effects? We know the drivers for marine energy. I've talked about some of them. It's climate change mitigation. It's providing energy for remote islands and other nations, and reducing fossil fuel use for everything from environmental health to human health, etc. However, stakeholders and their advisors have some concerns, and they're legitimate concerns. These are new kinds of devices with a new use in the ocean. That ocean is not being unused at the moment. There's many other users, from fishing to shipping to recreation, indigenous use, etc. So all that needs to be taken into account. And what are some of the strategies we can use? One of them is collecting and sharing information so that we can really understand how to move forward. Even the marine energy industry, the developers understand this is the time to collaborate and not compete yet if they really want to make this an industry and move forward. So a quick little timeout for an ad here. OES Environmental, Ocean Energy Systems, is one of the International Energy Agency committees of nations that come together to work on certain kinds of energy. And OES, or Ocean Energy Systems, has about 25 countries plus the European Commission who participate. And in 2010, they set up a task which examines environmental effects of marine energy in order to develop the industry in a responsible fashion. And that task is led by the US, by the Department of Energy, and it's implemented by my laboratory. And we call this task OES Environmental. We have been running since 2010. We work in 4-year phases, and we've just been re-upped for a new phase through 2028. At the moment, 15 countries in the European Union have joined us in this effort, and we are still hoping to bring a few more of the nations on board. I've got URLs all over this, and you can find everything on these TETHIS URLs. Okay, so let's talk about environmental effects. Let's go back a little bit. When this really started coming up, just before 2009, that's really when the modern age, if you will, of marine energy started. The thoughts then was, well, there aren't going to be any environmental effects. We don't need to worry. Everything's just fine. By that time, 2009 to 2011, suddenly stakeholders and regulators got wind of this and got very worried. Every possible interaction between a device and an animal or a habitat, the ocean, is going to be a big, high risk. And it's very different. If everything is a priority, nothing's a priority. We began to see the first papers come out that tried to sort of organize and categorize these. In 2011, we stood up TETHIS, our online knowledge management system, to curate and disseminate any knowledge that was available. And then from 2012 onward, we really tried to dig into some of these risks. We eliminated a few risks early on. There's very little chemical on board these devices. They're generally water lubricated, not petroleum lubricated, so that the chemical releases probably aren't a big deal, unlike some others like offshore wind, where there is a lot of petroleum on board. We also felt that these devices, tidal devices, are often underwater. Wave devices just have a device on the surface. The direct effects on birds probably isn't a big deal. And we started on our framework of what we call stressors and receptors. Stressors, and this comes from this original Bullard and Gill paper back in 2010. Stressors are those parts of a device or a system that might stress, injure, or kill an animal, destroy a habitat, interfere with an ecosystem or an ecological process. And receptors are the animals, the habitats, the ecosystem. It's those interactions that we really have to examine. You can't just say tidal devices are dangerous to whales. That gets you nowhere. You need to be specific about the pieces, the mechanisms, etc. And back in 2012 onward, we started gathering information from surrogate devices, wave buoys, or marker buoys that were out there, and so on, and did some in-water research studies, but there wasn't a lot to do. But in the meantime, we've published 3 reports in 2013, 2016, and 2020. We call the State of the Science Report, bringing together all the available knowledge. And I just want to, again, a little bit of an ad here. TETHIS, this is our online knowledge management system. You see the URL at the bottom. It's really simple, tethis.pnnl.gov. It's got a documents library that has over 10,000 documents that includes effects of marine energy, also wind. It's also got lots of other things. Events calendars. We have archived webinars for 15 years now, educational resources, etc. And I'd especially draw your attention to Tethys Blast, which is our every other week email newsletter that brings you new news and events in the industry, new webinars, job postings, conferences, new papers, etc. And Tethys is actually part of a larger system called Primer. And this is our universe of data and information. And again, the URL is pretty simple. It's over there in the lower right, primer.org. And 3 of the U.S. Department of Energy national labs, our laboratory, plus Sendia and NREL, we've run this system. And you see from that meatball thing over on the right, Tethys is there. Its sister system, Tethys Engineering, is exactly the same, but it's on the engineering and technology side with papers, webinars, etc., as opposed to the environmental, and there's many others. A projects database that allows you to go in and look at every project and company and deployment that's happened. There's a software hub. MHKDR is where the actual tabular data from all tests and deployments are, and then there's a GIS system. So anyway, it's an opportunity to just go into the center of Primer, use some key search terms, and get the kind of information you need, whether it's papers on one of the theses, some data out of MHKDR, maps out of the GIS system, etc. Okay, back to the topic of environmental effects. So we know this industry is in the early stages of development and commercialization, and we have seen worldwide through OES Environmental that these concerns are slowing permitting and development. We have seen a few projects that have actually been abandoned because they just can't meet what the regulators want. And as I mentioned, stressors and receptors. Over the last 15 years, we've brought this down to 7 priority stressor receptor interactions. The first is collision risk, and this is the toughest. The idea that you would have turning blades underwater and that animals might run into them, marine mammals, fish, etc., and be hurt or killed. This is a really hard one to examine underwater in these high energy environments. I'll get back to that later. Underwater noise, the noise from we're not talking so much about installation like pile driving, which we don't do much in this industry, but rather the operational noise, generators, PTOs, etc., that may disturb animals. Electromagnetic fields, particularly the magnetic field that comes off export cables. When you're moving power through a cable, you're creating a field, and only certain marine animals are sensitive, but the ones that are sensitive know it's there. Changes in habitat, both on the bottom where you're putting anchors and cables and so on, and also up through the water column to the surface where animals make their home. There are changes here. There are concerns among stakeholders that large marine animals, think about whales and really big basking sharks, could get tangled in some of the mooring lines. We personally believe that's not a very important risk for a number of reasons, but it's really stuck with a lot of stakeholders. So we have to look at it. Changes in oceanographic systems. You're taking power out, you're taking electrons out of the ocean. You may be changing circulation in tidal areas, decreasing the wave height a little bit. We can't examine this yet because we simply don't have enough devices in the ocean to show any difference against the natural variability of the system. So we rely on numerical models, hydrodynamic models, and there are a lot of those papers out. And the final one is one we're really looking to the future, displacement. What if we had hundreds of devices out there? What would happen when animals try to migrate by them? Would it be a barrier to them and so on? Again, we can't really examine that yet because we don't have enough devices out there currently, but we're gathering information where we can. So what do we need to do to actually measure some of these things to understand it? We have to have baseline assessments. Sadly enough, very few countries in the world, if any, know what their marine resources look like. What do the fish populations look like, the marine mammals, even the seabirds, etc. And what do they look like under changing baseline of climate change? But we have to get some idea so we can understand if changes have occurred. A few countries may ask for some pre-installation monitoring before you put a device in the water, and they pretty much all ask, once you put a device in the water, you need to monitor, you need to see what changes might be there. And all of this depends on having effective and consistent methods for data collection and analysis. And for those of you who are engineers, this is no surprise. You have to compare apples to apples. This is really, really difficult in the biological world. As I love to tell my brother-in-law, the high particle physicist, the physical world is easy compared to the biological world. You have to be comfortable with chaos to be a biologist. And it's very difficult to get people all using the same methods and the same instruments because there is so much variability. So we're working with that as best we can. We also need a way to deal with all this information, and we need to recognize that it has to be acceptable to regulators, stakeholders, etc. So we have worked a lot as OES Environmental between the data collection and is it used in regulatory processes. We've developed this process we call risk retirement. And that we define very carefully that for every new project, every interaction, you may not have to go back to square one and investigate everything, but you need to rely on existing data, on projects that have already been permitted, research, analogous industries. And all of this can be re-examined in future. So far, we have no more than 6 devices in the water anywhere together. So for those small numbers of devices, we feel fairly confident some of these interactions I've told you about aren't significant. And these colorful things is just our way of systematically assigning the data with some outcomes that are, in fact, understandable in the regulatory process. Regulators speak a different language than scientists, than engineers, than business. So I don't want to go into that too much. So I'm going to go back to my timeline. What have we done sort of in recent years? So in 2019, we applied this risk retirement concept first to small numbers of devices. And we went to a whole series, we brought together what we call our evidence bases, the most pertinent papers, data sets, etc. And we took them to a series of expert workshops. And so it's really on an expert judgment level. But we determined that underwater noise and electromagnetic fields from small numbers of devices could be retired. You should be able to use existing information to move forward. In 2020, middle of the pandemic, we did the same with habitat. The changes on the bottom, the changes in the water column, that we did online, needless to say. 2021, we did the same with changes in oceanographic systems for these small numbers of devices, because I mentioned we can only use the hydrodynamic models, but there is a good solid base of evidence. If you're running a hydrodynamic model and you want to show changes from wave devices or tidal devices, you need to put in literally hundreds of energy sinks in your models to get a change. So we felt pretty confident small numbers of devices would not have a measurable change. 2022, we're still working on collision risk, that one where it's really hard to say the animal won't get hit. 2023, we've done some more of these various pieces. And then in 2024, just finished up, we published our most recent State of the Science report. And I want to talk to you a little bit about that because that really it's an enormous report. It's over 300 pages. It has many, many authors and a huge number of contributors and reviewers. And it includes a vast array of information that we feel pretty confident when it was released in September 2024. It was absolutely the most up-to-date compendium anywhere. Each of these stressor receptors I've talked to you about, there is a lot of up-to-date information on these environmental effects, exactly what have we learned about animals colliding or not colliding with blades, what do we know about underwater noise effects, etc. And that's the biggest chunk of that report. We've also delved more into human dimensions, including what are potential social and economic effects and the role that stakeholder engagement plays in making sure you understand those. Because if biological sciences is chaotic, social science is affected by humans, it's about humans, it's even less easy to apply very strict rules to. Somebody raised a hand, yeah. Maybe a mistake. We'll wait.
Yeah, I don't think,
That was a mistake. Okay,
yeah, I think it's mistake.
thanks, Dibs. And then we put together a whole series of what we call community resources. Our risk retirement system, things like marine spatial planning, which many of you know. Some people call it zoning in the ocean. It's how you plan for uses. Also, the role that education and outreach plays with the general public and many others in trying to understand what these effects might be, and then talk data and information systems. We've also tried to look further. Now, I've mentioned that we only have up to 6 devices, and there's only one set of 6 devices in the ocean. But we're trying to look ahead to larger arrays of commercial size and take a systems approach. What will start to happen when we have many, many of these in the ocean? And I'll talk about those in a little bit. We also started to focus on tropical ecosystems because so much of what we've done started really in Europe and North America. It tends to be temperate areas, and tropical ecosystems work quite differently. So we need to be thinking about those as well, and then a path forward. That's the content of it. Now, it is a 300-page report. I've got a QR code for it a little later on. I'd encourage you to look at it, but if 300 pages is a little much, there is about a 12-page executive summary. We also create a series of what we call short science summaries. They're 1 pages, back and front, pretty pictures that gives you a quick summary of each of these topics: collision risk, noise, social, economic, etc. So it's a quick way. We originally did them to be able to talk to the policy level of government agencies, but they're a great quick way to get a sense of what's going on here. They're all up on Tethys. Okay, so back to our environmental effects. I want to show you, instead of just talking about this, I want to show you what some of this looks like. In the interest of time, I'm only going to talk about 2 of them: collision risk and underwater noise. So collision risk, what is it? It's the physical contact between marine mammals and moving parts of a device, generally blades, like a tidal turbine on the right here. And the animals we worry about are marine mammals, fish, seabirds that dive into the ocean for food, and also sea turtles. And this remains everywhere the biggest barrier to permitting, and that includes everywhere in the world. The reason this is considered to be such a high risk is because of uncertainty. Now, to date, we've seen no collisions of marine mammals, birds, or sea turtles. We have seen fish, especially in river turbines, maybe collide, maybe come really close. It's a very difficult environment to observe things. We've tended to use a lot of underwater acoustics, sonar, and things like that. But underwater video is becoming much more common. It's difficult. These are very fast-moving waters, needless to say, to generate power. They often are quite turbid or cloudy. And lights are a problem because if you use lights underwater, you attract animals. So it's very difficult to do, but we're getting better at it. And video helps tremendously, both identifying who it is, but also convincing people of that. If you look at 100 hours of video and see no animal near a turbine, it's not completely definitive, but it sure helps. And we're using AI wherever possible to try to recognize things on video so people don't have to look at 100 hours of video. We've tended to use multiple kinds of devices, multiple kinds of instruments to really get at this. One kind of instrument doesn't really work. There are models that have been created and are actually used in permitting processes in Europe. Collision risk models and counter risk models. They're not very good. They're not really fit for purpose, but even the best ones need data for validation. So they're really kind of a shot in the dark. Just to give you a little sense of it, if you're going to look at collision risk, you may need a whole array of different instruments. The most common one we're trying now is to use active acoustics, things like passive acoustics, listening for animals who are vocalizing, and then as they come closer, active acoustics like sonar, etc., acoustic cameras, and then handing off eventually right close to the turbine to a video camera. And if you can do that, you can actually follow the animal coming in and see what's really happening. We haven't been completely successful everywhere, but we're getting better at it. And to give you a sense of what that might look like, this is just a still shot off video on a cross-flow turbine. tidal turbine in our bay right off our laboratory on the Pacific coast. It's not turning right now, and you can see that harbor seal is pretty interested. Those harbor seals actually hung around when it was turning too. We saw birds chasing fish through the turbine, again, when it was not running, and we find that fish and birds tend to stay away. Some of the marine mammals are just a little too curious. Here we have another tidal turbine. This is in the north of Scotland, the Shetland Islands, Nova Innovation. And what you see is this grebe, really good picture of it, very close. The water's very clear there. And when the turbine is not turning like this, we see many, many fish, seals, and birds around it. As soon as the turbine starts turning there, they run away. So there's something to be said for the fact that they may be avoiding this just based on the amount of current they would have to swim against, which is not good for them bioenergetically. And this final one's a little harder to see, but this is in a river turbine in Alaska. And if you look over at about 2 o'clock, it's a crossflow turbine. Over about 2 o'clock, there's a little tiny silver streak. That is a salmon smolt that has just come through the turbine. And we have a lot of hours of this. And again, we see fish that seem to actually maybe get hit by the turbines, but they're not really harmed. So this is the kind of thing we're dealing with. And this is some of the best visuals we have. Okay, let's talk about underwater noise a little. We worry about noise in the ocean because marine animals communicate using noise. They navigate, they communicate, they do all kinds of things to find prey, much as we or terrestrial animals would use sight or light on land. They use noise in the ocean. So the more noise you add, the more you make it difficult for them to hear the right stuff. So this is why we worry. We know that the generators, the PTOs from tidal devices, wave devices, etc., create noise. So it's adding to what's already there. And it's mostly marine mammals. You probably aren't aware, a lot of fish species also hear and make noise. So they're also of concern. Now, what we have measured from wave energy devices and tidal devices to date has been very low frequency, low amplitude noise. We're also lucky enough that there is an international specification for measuring noise from these tidal and wave devices. And the US has some regulatory standards for both fish and marine mammals. So we have something to go on, which we don't in most of these other interactions. So far, every device that we have measured and has fallen well below those levels of concern. So we have considered this retired for those small numbers of devices, but with a series of caveats that every new device should be measured for its noise output across a broad spectrum of frequency and so on. This is some of the sorts of information you get out of this. Now, the left-hand file here, the top half is showing sources of noise in the ocean. You'll see some are biological, some are physical, some are from humans, some are marine energy devices, those teal ones in the middle. And they're showing across the frequency spectrum from about 1 hertz up to about 1,000 kilohertz, sort of across the middle there. The bottom half of it is the hearing range of marine animals. And what you can really take away from this is that no matter what frequency you would put noise out in, somebody is listening in the ocean. So there isn't a key frequency you can say, if we stay at that frequency, no problem. So we need to work around this with amplitudes and so on and learn more. The right-hand panel, I just want to point out one of the new areas we're looking at. Everybody knows that sound is a wave, right? It's going through the ocean. As it goes through the water, it excites particles, and you get particle motion from this sound as well. This matters because certain fish, those with lateral lines, detect sound as particles, not as the wave. So is this a problem? We don't know. The particle motion does not propagate nearly as far as the wave, but and we don't have very good ways to measure it. So this is one of the areas where we're looking at. We doubt it's a huge problem, but we need to look at this and probably develop the right instrumentation to be able to measure it, at least so we can say this is not a problem. So that's the kind of thing that we're sort of faced with. So I want to just spend a few minutes talking about people, social and economic effects. when you go out and talk to stakeholders, very often they will talk about environmental effects, but as you dig down, you find out it's really the use of the environment that they're interested in. So they get very confounded with social and economic concerns. There's not a lot of research in this area, not a lot of great methods. We know that there are interactions of marine energy with fisheries and ports and supply chains and tourism and so on and so forth. We know there are benefits that come with marine energy to an area, employment, economic development, and so on. But there's also potential effects on social and economic systems, schools, social services, the cost of housing goes up, et cetera, et cetera. And we don't know enough about this. We do know that you need to engage with stakeholders early and often if you want to understand this. And one of the areas we've tried to both document but move forward in is education outreach and workforce development. The general public doesn't know a lot about marine energy, and we need to find ways to reach these diverse audiences. We know that education and engagement can help fight misinformation, opposition to projects, and we also know it can bring more young people into this workforce. So we just have a large a chapter in the State of the Science that goes through a lot of this and provides a lot of those sorts of details and connections throughout the world to where there's good information. We've also done a number of things ourselves. We've created coloring books for very young children, video series for the public. We've got a video game actually out there for collision risks that I would strongly advise you to give it a shot. It's both one for fish and one for marine mammals. It's a find your own adventure. As the animal's swimming towards the turbine, it decides what to do. That's you deciding. So there's the QR code. If you have any interest, it's kind of fun. And we're always looking for feedback on things like that. Okay, now I mentioned we had been talking about just very small numbers of devices up to 6, but we're trying to look ahead for these system-wide effects. And we have 3 areas we've worked on. One of the papers is already out, the other 2 are under review. And just to give you a sense, this is a terrible thing to look at, but on the left, one of the things we've tried to do is say we've learned a lot about these stressor receptor interactions for small numbers of devices. What happens when you go to large numbers, 30 devices or more? Are the effects additive? Are they multiplicative, synergistic, etc.? And so we've tried to kind of parse that out. That's the paper that's already out in, I can't remember the journal, anyway. Secondly, we've looked at some of the ecosystem models that exist for the ocean, particularly around fisheries. So there's a sense of how the different components of the ocean interact. And as you extract fish from the ocean, what happens to populations and communities. And we have added marine energy to those models to try to see if there are other kinds of interactive effects. And that paper's under review right now. And thirdly, cumulative impacts. How does marine energy add to other human activities, shipping and boating and tourism and etc. And oh dear, didn't mean to do that. Got to go back one. Sorry. Oh shoot. There. And so again, we've tried to look at which of these are additive, which are synergistic, etc. And that's a great paper, and it's under review right now. So just to try to think about system-wide effects. Okay. And finally, we've tried to look at effects in tropical and subtropical ecosystems because we have been very sort of northern and a little Australia focused. We know that there are more and more countries in the tropics that are interested in marine energy. Tropical ecosystems have much higher biodiversity than do temperate ecosystems, and they have unique habitats, things like coral reefs and mangrove swamps, etc. We also find when we talk to many of the tropical countries, many of which are smaller countries, that social acceptance for development is very tied into ecological health. So we really need to rethink the way we address things. Our standard stressor receptor doesn't really do it. We have to look at whole ecosystems. So we're working on that one. Okay, starting to wrap up here. This is just sort of the timeline of what we've been doing over our first 4 phases. We've made some progress. We've put out these State of the Science reports. As we move from 2024 to 2028, we'll be continuing to do what we're doing, but we're trying to take on 4 additional areas. The first we are calling environmental acceptability, which is still a term we're struggling with. But the idea that we have all this vast amount of information, how do we turn this around into proactive guidance for developers as they design, prototype, fabricate, deploy, operate, maintain, and then decommission their systems? How do we decrease the environmental footprint from the very beginning? So, and if we are successful, eventually something like sort of a good housekeeping seal of approval. You as a developer have followed all these steps. We will work with the regulatory community too to say this makes this better. We won't put them through quite the same, gauntlet of monitoring and spending money. Secondly, we've been looking more at off-grid uses. The regulatory system is really set up for big devices to generate power to the national grid. But so many of these marine energy devices, tidal and wave, will work better in small islands, at sea, etc. And we're trying through a series of use cases to see if we can get a better sense of what those effects might be, and therefore affect the regulatory process. Again, maybe they don't need to go through the years and years long spending of money on monitoring if it's not necessary. So that's the object there. We'll continue to work on both social and economic issues and take the next steps on this sort of system-wide. We've done the 3 journal papers, sort of the theory of it. Now we want to try to apply it. So that's just about it. I'm sitting here talking to you, but this takes a global village. I have my very talented team at PNNL, but I want to note that of the 15 countries involved with us in the European Union, there is a representative from each country who participates with us, and they are very hands-on. We do a lot of the final work, but they are very involved in scoping, in writing, in reviewing, etc. And we couldn't do it without them. And that's frankly one of the funnest things about this. So at that point, I want to say thank you. There is the QR code for the State of the Science report, if you'd like to look at that. And I see lots of hands, which is exciting. I want to answer some questions. So
Yep.
I'm going to cut out this. Can you still see that final slide? No.
We can't, but
Okay.
I
You got
guess
it. Oh,